Okay, here I go. Half-life and stuff. Next. Half-life is defined as the time required for 1/2 of a reactant to react. Half-life graphs, you'll get one on the AP test. It's like 100% guarantee. They're super easy. You go to where there's half of what there was at the start, and then you go down to the time, and we could say, hey, that's 12,000 seconds. Like that should not be hard at all, reading a graph. Okay, so half-life, there's the definition. Because the concentration of A at T 1/2 is 1/2 of the original, AT equals 0.5 A naught. That's not impossible, correct? So AT, that means the concentration of A at a specific time, and this is half the time, or the half-life, it's equal to 0.5 of the concentration of the original. Kind of all right so far? Okay, we're going to do some math. We won't do it, but it's just going to talk you through and be like, hey, since that is that, and the ln of that is 0.693, then yada, yada, life's great. So just that's coming up. But it's based on the fact that that's equal to 0.5 of A naught. Okay, for a first order process, if we do math, like we take the integrated rate and we plug it all in, we end up with ln of 0.5 A naught over A naught equals negative KT. All right, now we can cancel these things out, right? So we have A naught on top and on bottom. So really the ln of 0.05 is equal to negative KT 1/2. If you actually find that value, it's negative 0.693. So this isn't a number we made up. It's the ln of 0.5. And so we then solve, or sorry, that equals negative KT. If we rearrange it, we bring K under, or negative K, that makes it positive. And so now we have this extremely simple equation to use. You don't have to have it memorized. It's given to you, but it is the half-life. The time for half of it to disappear for a first order reaction, only first order, is equal to 0.693 divided by K. So this is an extremely common thing to come into one of these problems after we've found the order, then we've solved for K, and then we're going to find the half-life because it's just 0.693 over that slope. With me, or the negative slope for this one. You all right with that? This is given to you on the AP test. And I just looked, and on the explanation from 2021, it only includes first order. All right. Now, this is pretty interesting, and they test this often. So for the first order process, the half-life is not dependent on the concentration of A naught. It doesn't matter what we start with. The time it takes for half of it to disappear is always equal to 0.693 over the rate constant. Okay, for a second order, it does matter, because second order, we start getting into exponents and things like math blows up. You okay with that? So we have a half-life for a second order. We won't spend as much. I mean, we'll do it, but I'm not going to test it. I see people writing, so I'll hang out for a second. Well, let's actually go back for a minute. Let's find one of these that was first order. So this one was first order, right? So if I were to ask E, what's the half-life of this, you could do that pretty easy, because look, we already have what? We already have K. We know it's a first order reaction. So to find the half-life, I just take 0.693 and divide it by 0.029, and that will tell me what the half-life is. What did I end up with? 0.9, 23.9. So it's going to take 24 seconds, or sorry, minutes. Yeah, just look right here. You can double check also. Half of 0.0165 would be 0.08, right? And we were saying it's here. Is 0.008 in between these two? Yeah, so it's probably, it's reasonable, so it's probably right. You okay with that? Like that one should be money. If you get K, you can get half-life on first order. Okay, coming back. Uh-oh. Hold on. Where's the second order half-lives? Well, maybe I realized they weren't on the test last year and got rid of them. Okay. Oh, there, I just went too far. So here we go for a second order process. And don't write all this math out. But for a second order process, we have a different integrated rate law, right? That means we have to plug in different things. And so we end up with the half-life being equal to 1 over the original concentration times K. So notice for a second order, the half-life is dependent on the concentration that you start with. Okay, so this is the only part you need to worry about. T1/2 equals 1 over K times A naught. Okay, I'm going to go back. Let's find one that was second order somewhere. Nope, it was this next one. So this one was second order, right? How do you know just looking here that this one was second order? The exponent, correct? Okay, so what's the half-life then? See if you can figure that out. This was K, by the way, if you don't remember. All right, I didn't type it in, but I wrote it out. 1 over K times 0.5. Are we all right with that? Any questions where I got either one of those two numbers? I know it was 0.002098. I just rounded it to 21. If you're okay with that. Okay, anyone have an answer for me? What this equals? I'm going to guess 9,000. Am I really good at math to do that in my head? No. The answer was right there, but that's okay. The process, are we okay with typing it in? It's a little different based on our rounding earlier in the process, but it should be right around 9,000. You didn't get anything close to 9,000? Okay, hold on. Oh. The whole, you need to have those not both in separate ones. Okay. With Half-Life, not that bad, correct? You need to know, oh, I'm flying through. You need to know what it looks like on a graph, like how to identify it. So you'd have something here. If it was at 0, like if this was 100, then you would find where 50 is, and your half-life would be down there. Like the easy part, you have to know that. Then you also need need to know how to find it based on finding K. Yes.
Before we do any math, we should just look and see if they actually give us the answer.
I would for sure, because you might. You can also trace it on your calculator if you know how to trace a line. You can go down to exactly half of what it was, but that would take you as much effort as typing 0.693 divided by K. So do your TI-84s trace a line? Yes, okay. Okay, I did something wrong. It will self-destruct in 30 seconds. Thanks for the burrito this morning, by the way, all you FFA kids. All right, now here is the paper. You will get it's a reference sheet I'll give you for your exam. Someone cry? All right, so it gives you the integrated rate laws for 0, first, and second order. And we've never talked about 0 order, have we? Okay, hold on. I don't usually spend that much time on it. If rate equals K times something to the 0 order, what does 0 do to whatever's in here? Makes it 1. And so what that means fundamentally is that the rate is independent on the concentration of that substance. Like it doesn't matter how much there is of it. So like when we put magnesium in hydrochloric acid, there is not a concentration of magnesium because it's a solid. The rate of the reaction is determined by the concentration of the acid. So we'd say for magnesium, it would be 0 order. Does that make sense? Seth? No? Okay.
If it's 0, then we don't actually need to worry about it.
Yep. So we have our magnesium. It might ask you some math, but almost never ever does it, because changing, if I had a bigger block of magnesium, it's not really changing the concentration of it because it's not even in an aqueous solution. Yeah, it will a tiny bit. So that is true. But it's really actually going to slow it down more than speed it up, because there's less surface area per particle in a bigger blob. But anyway, just ignore all that. The concentration of the hydrochloric acid out here is more important to the rate than the concentration that doesn't technically even exist in a solid. So if we were going to write the rate law for this, we'd say rate equals K mg 0. We wouldn't really even do it. It's just an example. And HCl to the first, probably. Like we'd have to study to make sure it's a first. It could be whatever it wants to be. But this would mean that the rate is independent of the concentration. All right, so I wouldn't stress a ton about these because rate is just equal to K. All right, then there's the math if you feel like it. Then first order rate is K times A to the first. All right, there was our integrated rate law. This is the same rate law, just moved around, because if you subtract LNs, you subtract or you divide them. Do you remember that from math, whatever? I don't know, it's dumb. But like, this is plus ln. To get KT alone, you subtract ln, which is over here. And really subtracting is putting them, they're dividing. That's algebra. Equals KT, yada, yada. These are all the same. They're just, I don't know, manipulated differently. Okay. Plot needed to give a straight line, A versus T. ln of A versus T, 1 over A versus T. All right, relationship of rate constant to the slope of the straight line. Slope is negative K, slope is negative K, slope is K. And then there's the half-lives. And these won't be tested. So, I mean, you'll get this exact piece of paper when you do your test. The test is not tomorrow or Friday, so don't have a heart attack.
Is it on Monday?
That's when I feel like it. Now, we still have a whole concept to do in this chapter. Yeah, it feels like it should be over, right? But it's not. We're on slide 73 out of 128.
Great.
So it's not bad. This is an entire unit of 8 of them on the AP test, just chapter 14. It's the most AP questions per one chapter that exists. There's 10 subsections of chapter 14 or unit 5, I think, which is all in this chapter, which is kind of nice because a lot of them are like 5 different chapters and you got to bounce around. This is just chapter 14. Now, there's a lot of it, but we can live. All right, let's see what else we got here. We got Half-Life, we got that. Okay, temperature and rate. This isn't math, Sarah, so you'll be fine. You'll be okay. All right, temperature and rate. This is a qualitative concept, which means no math, and it's not hard. The hotter something is, the faster the rate. I feel like we're ready for that.
So the warmer it is, the brighter it glows.
There you go. Okay. You blow more air in, it gets hot, and it burns the stuff faster. Okay, look. Generally, and this means generally, it isn't 100% of the time, but it's most of the time. As temperature increases, so does the reaction rate. Okay, and then the reason why, this is because K is temperature dependent. So AP requires you to know that K is actually temperature dependent. So when you read a problem on the AP test, it will give you the temperature that this reaction is happening at. It doesn't matter at all to you, but K would be different if it was at a different temperature. All right, so don't worry that there's a temperature given in the problem. It's just because those are the conditions the problem is happening. You should know a couple things then. The hotter, the faster the rate. K is temperature dependent. All right, it also has to do with the faster things are moving, the more particles have the energy needed for a reaction to happen. You with me? Okay. All right, that was easy. Let's see this graph. All this is showing you is as temperature increases, the number of particles with the high energy increases. So the reaction's more likely to happen. Okay, next, this is actually on the AP test, and you should be grateful because all that hard math you did will be worth a point. A question like this will be worth a point. The collision model is super, super simple to understand. It says in a chemical reactions, bonds are broken and new ones are formed, but they can only react if they touch or collide with each other. It's literally like saying, if you have a chemical here and a chemical here, they're not going to react unless they touch. Okay? If they actually interact, then they form. Like they have to have energy, but they have to touch. That's called the collision model or collision theory. I don't know. I call it the collision theory. This book obviously calls it the collision model. The reason it's not probably a law is because we can't like literally observe one atom colliding with another atom. It's pretty hard to do. Okay, so all we're saying once again is in order for AB to form, A and B have to have been together. Crazy. It's like not hard. Okay, yes, way.
That is beyond my.
All right, now the collision model. There's more to it, but not much. Furthermore, molecules must collide with the correct orientation and with enough energy to cause bond breakage and formation. So they have to touch, but they have to touch in the right orientation and have enough energy. So this beautiful picture up here is a Lego. Yeah, it's not the Titanic. All right. It's drawn for you, so you realize Legos only snap together if they have the right orientation, right?
Oh, yeah.
So inside your box of Legos, most of them aren't stuck together, even though they're in contact. That's because they either A, didn't have the right orientation, and even if they did, no one put the force in to push them together. You with me? So in order for Legos to stick together, they got to get close. They have to have someone push them, and they have to be oriented the right way. Easy enough? That's the collision model. This is so fun. Good? Do I not see him? I've driven every morning this week, and that was after coming back from a vacation that I had to wake up early on Sunday after. I've just never caught up. It's Wednesday. Yeah, imagine how hungry I'll be on Friday. You could get a concussion. Yep. Nope. All right, ready? Next. Activation energy. These are all just money things. Let me go back and delete this slide because it has nothing to do with this class. That was from a different one. Activation energy. All right. So this follows the previous slide. And it says, in other words, there is a minimum amount of energy required for a reaction to happen. If you don't push the Legos hard enough, they'll never stick together. In chemistry, if they collide but don't have enough energy, the reaction never actually happens. We have to reach what's called the activation energy for a reaction to happen. Okay, so just as a ball cannot get over a hill if it does not roll up the hill with enough energy, it would just come back, right? A reaction cannot occur unless the molecules possess sufficient energy to get over the activation energy barrier. So that's why we heat a lot of things for a reaction to happen. So when I burned the magnesium a while ago, I put it in the Bunsen burner so that I would raise the energy of the reactants from here at least to here. And once I got there, you notice it started to react, and I took it out of the Bunsen burner. I didn't have to keep burning it because once it got to the top of the hill, all the rest of the energy was free. Like it was going to come out from the bonds being broken and formed. You okay with that? Okay. Reaction coordinate diagrams. Haven't we already done these? Have we? They're the same. This looks more complicated than it needs to be. These are on the AP test, and they're not math. Hallelujah, right? A reaction coordinate diagram, I feel like we already did. It shows the energy versus time as a reaction proceeds from reactants. Okay. This is the same thing. It looks different because they are just like drawing out what the reactants and the products look like, but it's the exact same thing. Okay. You need to label it or even draw one given words. Okay. So I'm going to say this out loud, so please listen. You ready? I want you to draw an endothermic reaction curve. So draw an endothermic reaction curve. Okay. Now, I want you to label the following numbers. It had an initial energy of 20 joules. Its activation energy was 12. Now, your picture, you're like, that isn't to scale. It doesn't matter at all. And then it lost an overall loss of energy of 5 joules. So what is he talking about, right? Okay, check and see if your curve looks like your lab partner's curve. Okay, how we doing? Okay, here we go. Check your work. Check your work. It may look weird because the scale's off, but you should have that shape where it ends lower, correct? Oh, did I say endo? Okay, my bad. My bad. Sorry. Okay. I do the same thing in normal chemistry like 2 days ago, and I did exo, so I apologize. All right. So what would be right here? 20. Then what would be the top of this barrier here? All right. And then I don't remember the number. What did I say? All right. So I said it lost 5, which meant it was exothermic. So I needed to say it gained 5. I apologize. So now this would be here at 25. Now, did anyone put 27? That's because I was confusing, right? So let me start this over again. This is what happens when you're on Mountain Dew. All right. The overall change in energy is the final minus initial, right? So I said it was endo, but then I defined the numbers as exo. So I should have said it gained 5. Now, we never measure like the loss from the peak of the activation barrier to where it ends. That's not something we calculate because that energy never really existed to us. It's always measured from where we start to where we end. And that was not my best teaching moment in my life. Thank you. Okay, let's see if I have one typed out. Oh, I don't. That's okay. That's right. I must have been talking about catalysts and anti-catalysts. So a catalyst lowers the activation energy, making the reaction happen faster. Like preservatives in your food, well, they are like anti-catalysts. They raise the activation energy, so the reaction takes a long time. Does that make sense? Yada, yada. Anyway, that's what that picture must have been. All right. See, I did it a year ago, even I did exo. Why did I switch to endo? That was stupid of me. This is what we're going to do here. I got a lot of the same things. Okay, here we go. This is in words, so I can't screw this one up. Methane reacts with oxygen in a simple combustion reaction. Now, you don't have to write out and balance that or anything. It's just telling you that's what's happening. The activation energy is 22 kilojoules, and the reaction releases 80 kilojoules. Draw the reaction coordinate diagram. Now you might be frustrated because it's missing a number, but do you care? Not really. Just start where you feel like, but you better start at least higher than what number? You better start above 80 because you wouldn't get into a negative on your graph. You could. I would personally choose 100 because that's pretty easy math. Great minds think alike, Timmy. I was holding my horse. All right. Raise your hands if you're ready. The back row. I got a Delaney in my online driver's ed class. Is that your little sister? Okay, here we go. I'm going to draw it out. Maybe it's already drawn out. Looks like I cut the top off at some point in time on accident. That makes no sense, but that's okay. What would this number right here be? Fair enough. No, no, that's what I was trying to stress that I screwed up last time. The change in energy is always from where you start, never from here. Because I had to put this energy into the system, and we just want to observe the changes of the system, which would be from where it started to where it ended. It was tricky because I screwed up that last one. Thank you for your patience. I feel so absolved. Okay, easy enough. You'll have to draw one of these on the test from words. Piece of cake, I hope. All right, yada, 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 yada. This is just going back. Don't stress a ton. It shows the energy of reactants and products over time. The high point on the diagram is the transition state. That is a key word. The species present at the transition state is called the activated complex. So like right here, the reaction is going to happen. That's the transition state. That's when actual reactants are transitioning to actual products. All right, just know that. So that transition state is the activated complex. Oh, we're not out of here in 4 minutes, are we? We're out of here at 1. Okay, I just thought we were out of time. Sweet. We're cruising. Look, we were on slide 73 to start, and now we're where? 92. I feel good about that. Okay, ready? All right. Whatever, hold on. Wow, are these all review? I don't know. This must have been in response to previous years needing help. Do you need more, or should we go on the reaction mechanisms? All right, someone said go on. So that's the person I'm going to listen to. Whoever said it was the one I wanted to hear, so it was perfect.
I think we should go on.
There you go. Thank you.
Is that like one of those questions where there's only one right answer?
Yep. It's called a parent question. Yeah. My answer to that was always no. What is it?
Yeah.
Yeah. Oh, that's even better. My children is, oh, I did them like 3 years ago. I'm like, oh, I hate you all. I don't actually, I love them all. Yeah, good point. Okay, any idea what VIP stands for?
Very important personnel.
Close.
Very important process. Very important product.
Principle. Very important principle. This is on the test a lot. And the good news is, in my opinion, it's a lot easier than everything we've done. Not what we just did, like drawing that graph, that's pretty easy. This is easier than the math. Okay, now reaction mechanisms in the next 10 minutes might not make a ton of sense, but by the end of tomorrow, you'll be like, oh, those are easy. They are. Okay, reaction mechanisms is the actual sequence of events that describe the process by which reactants become products. All right, so follow me here. The reaction mechanism will show you steps that the reaction took. So I made this up, but it's not super hard. The overall reaction, like we've been writing, would just be this, like A plus B plus C goes to ABC. And we've been doing that all year and we're fine with that. The reaction mechanism is going to show you the steps that happen for that to happen. Look at the screen. So in order to make A, B, and C, the first step is A and B combined to make AB. Well, that's not rocket science. You okay with that? So like everything's bouncing around and A and B come together. That's the first step of a multi-step reaction. And now that we have AB, it runs into C and we end up with ABC. Who's with me? Okay, that is not impossible to understand, I hope. In these reactions, and we've done something similar to this, we have what we call intermediates, which are substances that are not represented in the overall reaction, but are written in the steps. So what is not written here, but is here? I didn't do very good. AB. AB is produced in one step and consumed in the next, and we call that an intermediate. It existed for a second, but then it bonded with something else. Go ahead.
But it can't go from B plus C, BC, and A plus BC. Can I do that? Is it interchangeable?
Like, not really the way I wrote it. If I wrote it a different way, sure, because I made this up. But really, in chemistry, what if this was true? A and B had to be together first to like give the surface for C to even stick to, and C won't stick to A or B, but only when A, B come together. If that kind of makes sense.
Yeah.
Go ahead. That'd be taken care of in the balanced reactions. Because there wouldn't be excess AB, there could be excess of my original reactant, but not AB. That's a good question. And that's why there's just weakness of just making this crap up. All right, now that's the nutshell. We'll go a little bit deeper. So reactions may occur all at once or through several discrete steps. So you might jump all the way from the bottom stair to the top, or you might walk up all of them. That's all. Each of these processes is known as an elementary reaction or elementary process. Okay, now for a second, I'm going to go backwards and then I'll come back. So what we're saying is, this is my overall reaction. And then these would be my elementary processes. You okay with that? Okay. There's not a ton on this slide that you need to write down, so don't spend too much time on it. It's just, I guess it introduces a new word called an elementary reaction or process. And those are the steps taken for a reaction to happen. All right, let me move on in a few seconds. Look at that, all the snow's already gone. That's good, because wait a minute. Oh, never mind. It's the 16th. I was in charge of snow cleaning till the 15th. It can snow all at once. I don't even care. Sucks to be the old man. Wait, I am an old man. All right, moving on. Okay, don't write every single thing here. Just kind of look at it. So the molecularity of a process tells how many molecules are involved in the process. Okay, so we have what we call a unimolecular process. And that is when A goes to products. This would be called a decomposition reaction. It's where one thing just breaks apart. And A, it makes products, and the rate is equal to K times A, raised to the first. A bimolecular, and there's two ways to have a bimolecular, is when two molecules interact. Okay, bicycle, two wheels, right? So bimolecular means two molecules. The two ways that it can happen are that two of the same thing can combine to make a product. So like chlorine plus chlorine goes to Cl2. All right, the rate for that would be Ka to the second, because there's two things involved now. Our exponent and our mechanism and molecularity are all going to be tied together. Okay, and this will hopefully make a lot of sense after we're done tomorrow. The second way to have bimolecular is to have A plus B making AB. And the rate law there would be rate equals K, A, and B. Both of these reactions right here would be second order reactions. The overall, they'd be second order, because we have one thing that's second order here. And so that's just two. If we added two plus, there's nothing else. So two things each to the first adds to two. So they're both second order overall. Okay. Now there are things called termolecular, and these are really rare. Termolecular requires that you have three things that all run into each other at the right energy and orientation at the exact same time. That's kind of hard to get three individual things to run into each other at the exact same perfect time. So they usually have pretty slow rates. But termolecular, you could have AAA, AAB, or ABC, or you could have ABB or whatever. But it's three things that are required to collide at the same time, and they're rare. All right, the only thing the AP test requires is that you know that ter or tetra or whatever are really, really rare. But it expects you to know uni and bimolecular. Uni means one thing breaks apart. Bi means two things are involved, two of the same thing or two separate things. Okay. Now, multi-step mechanisms. In a multi-step process, one of the steps will be slower than all the others. Okay, and I'm going to put this into my family. When we get into the minivan, Jace is always the slowest. It does not matter how fast the rest of us get into that minivan, because we always have to wait for Mr. Slowski. Go ahead.
Isn't that how life works? Like if there's a bunch of things that all have different rates, there's going to be a slowest one.
Yep, it's just order the way it is. And the rate is determined by the slowest, not the fastest. Okay, another thing, well, this is my pet peeve, but in track we used to run what's called the medley. And it was a 200 runner, a 200 runner, a 400 runner, and an 800 runner. And guess what? No one gave a crap how fast the 200 runners were, because the 800 runner ran the slowest. Now they could be really fast 800 runner, but no matter what, they're running way slower than a 200 meter runner, right? So that race only ever mattered how good your 800 runner was. It was the rate that person determined the overall rate of the reaction. In our steps, we will always have one of the two or three or four, whatever, that's slower than the rest. And we call that the rate determining step. If you have a job like you have to clean, you got to brick the oven or whatever you guys call it. Something is slow. You know it is. Like when you close, there's something everyone hates at their job to do. And that's the slowest part. You know it. Everyone has it. When you drive, we don't have a lot of toll booths here in Brigham. We have stoplights, right? You can go 35 down Main Street, but really the light which stops you, if you hit 3 of them, that determines when you get home, not how fast you drive between them. Are you okay with that? Okay, so the rate determining step is the slow step. All right. Whoa, ha, I have complained about the medley before. I've even told a story when we went from 1st to 9th because our 800 runners sucked. All right, I won't use names because that person's sister is now in our school. All right. The order of the reaction can give you clues about the mechanism, and the mechanism can give you the order of the reaction. We'll talk about this again tomorrow. It's about time, and it's a good cutoff. Tomorrow, we're actually going to do an activity, which we hardly ever do. We're going to make widgets. Don't look at me that way, but you're going to hate it. I mean, love. I meant to say love.
Wow.